So this is the first lecture on time series data. Here I have an example of time series data. This is long-term interest rates in Germany starting at January 2000 when it was 5.54%, going all the way to 2017 January when the interest rate was 0.25%. So what's special about time series data compared to cross-sectional data is that there is a natural ordering of the observations. And the ordering is, of course, time. When we have cross-sectional data, there is no specific ordering. If I have observations for individuals or firm or countries, I can sort and organize the data in any way I like. So for time series data, I will call this first number, assuming that this is the variable that we're trying to explain, I'll call that y1, just like we did for cross-sectional data. The second one will be called y2, and so on all the way to the final one. For cross-sectional data, we almost always use the symbol n for the number of observations. With time series data, we change this and use the symbol t instead. So capital T will be the number of observations. In this example, it goes from row 2 to 206, so capital T is 205. In cross-sectional data, we denote an arbitrary observation by y subscript I. For time series, we switch this and denote an arbitrary observation by y subscript t. So for example, this is yt for small t equal to 6. So to summarize, we have our sample. It's denoted by y1 all the way to y capital T. Capital T is the sample size. We never reorder the sample. Time will always be our ordering of the sample. If I want to refer to an arbitrary specific point, sample point, then for time series data we use the symbol T instead of the symbol I, and that's mostly to remind us that we're dealing with time series data and not cross-sectional data. It's of course not important per se, we could use any symbol we like. Similarly to the idea behind cross-sectional data, we will view this number here, y1, as the outcome of a random variable. So our view here is that there is a random variable determining the German long-term interest rate for January 2000, which we call y1. This random variable has a particular distribution, it has an expected value, a variance, and so on. And at January 2000, we actually observe a specific outcome. So at January 2000, y1 is 5.54. But before January 2000, y1 is a random variable. So in this sense, just like for the cross-sectional data, we simply view all these numbers as drawings from a sequence of random variables. So the idea is that I have a sequence of random variables going from y1 through yt. I perform the experiment by letting time go, and y1 returns a number, say 5.54, y2 returns another number, 5.51, and so on. So even though it's kind of a philosophical discussion, we sometimes view this particular set of data as just one particular realization of the sequences. We can think of going back in time and restarting time at 2000 January and letting time go forward again, and then we would get a different sequence of numbers, a different realization from the sequence of random variables. So this is actually crucial because it will be part of the model building in time series models. That the sample that we view, y1 through yt, is viewed as a sequence of random variables. Now, whenever we have a sequence of random variables and it's over time, then we often call this sequence a time series process or a time series sequence. Remember that when we have cross-sectional data, then we are typically allowed to make the random sample assumption. If you remember, the random sample assumption assumes that this sample that we have is a sequence of IID random variables, independent and identically distributed random variables. Basically, we're saying that if I have cross-sectional data, then the observation of one individual is completely independent of the observations of another individual. So let's ask us the question whether this is a reasonable assumption when we have time series data. So what we need to ask ourselves is the following. If I look at the interest rate at a particular point in time, say March 2000, is this observation, is this random variable that generated this interest rate independent of the one the following month in April? So independent means that they are completely unrelated, nothing to do with each other, and the information about the outcome of this one will not help us in any way to predict the outcome of that one. For this particular data for interest rates, that is definitely not satisfied. There is actually a very strong dependence between interest rates over time measured at different months. If the interest rate is particularly high this month compared to sort of a normal interest rate, then it's very likely that it will be high the next month as well. We can see that this is precisely what is happening in the beginning. In the beginning of the sample, beginning of 2000, the interest rate long term was very high. Moving on to 2015, 2016, the interest rate is very low. So we have to conclude that at least in this sample is definitely not a random sample, and this is the reason for why time series data is in general much more difficult to analyze than cross-sectional data. There is a lot of topics that we have covered where the assumption of a random sample is built in. So we, in a sense, must start over again with econometrics and see what type of models we can build and what type of results we can find if we no longer can rely on the random sample assumption. Now, this of course doesn't mean that all time series violate the random sample assumption. Just to give you an example, let's say you toss a die every day and you write down in a journal or something the outcome of that toss. That will give you a time series of data, and that data you can still make the random sample assumption. There is no reason why the outcome of the die one day will affect the outcome the next day. But for most economic data, there is clearly a connection over time. For example, in GDP, investment, consumption, inflation, firm production, individual income over time, and so on. So let's state this with slanted text. With time series data, it is no longer reasonable to assume that the sample is a random sample. We cannot assume that our sample, viewed as a sequence of random variables, is a sequence of IID random variables. In most cases, there is definitely dependence between two sample points, at least if they are close in time. So we now lose this important random sample assumption and we have to replace it. Unfortunately, this will not be with just one simple assumption, but with a lot of different assumptions which are applicable in different cases. The most important one for time series data is the assumption of stationarity, and that will be discussed in a later lecture.